Hello and welcome. Today we're going to be discussing the problem Moo Hunt. In this problem, there is a string of length n filled entirely with m's and o's, but we don't know what it is. And we are given a bunch of moves. Each move consists of three values, x, y, and z, and we call a move successful if the letter at position x plus the letter at position y plus the letter at position z is equal to the string moo. And we are going to be given k of these moves. And given k of these moves, we want to determine two facts. First, we want to know what is the maximum number of successful moves. And secondly, what is the number of strings that actually obtain this maximum number of successes. And there are two important things that we need to know. We need to know that n is very small. N is at most 20, so the length of S is extremely short. And the number of moves that we are given is 200,000. So we have a lot of moves on a very short string. And since n is so small, we should start thinking that maybe we can afford a brute force algorithm here. In particular, perhaps we can brute force over all copies of this unknown string s. But before we get into that, let's look at an example. Suppose we had the string s is equal to moo moo. Again, s could be any length n string formed of m's and o's, but we're just going to analyze one example for now. And we're going to see that suppose our move was 1, 2, 3, then those letters in that order form a moo, right? There's an M in position 1, and then there's an O in position 2, and an O in position 3. So that's a success. If, on the other hand, we were looking at the move 5, 3, 6, then that would be a failure. 5 is an O, 3 is an O, and 6 is an O. So we fail. If, on the other hand, we were given the string moo MMO, then both of these moves would be successful. So 1, 2, 3 would still be moo, and 5 is now an M, 3 is still an O, and 6 is now still an O. So we also get moo here, so we get two successes. So this would be a better string than this one because we get a larger number of successes. So the maximum number of successes for these two moves is 2, and this would be one example of a string that achieves the maximum number of successes. In order to complete the problem, we wouldn't just want to find one example, but instead we would want to find every possible example. So what we're going to do in a question like this is we're going to begin by thinking about what is the naive brute force algorithm, right? What's the simplest idea that we could come up with? And the simplest idea that we could come up with is simply loop over every possible value for the unknown string s. And for each of those unknown string s's, we're going to loop over every single possible move and check if that move is successful. If it is, we'll increase a counter and we'll save the maximum count. And we can also save the number of strings that actually obtain that maximum count. However, there's a small problem with this naive brute force algorithm. The first is that this loop over all possible values of s is exponential in runtime. So for the first character in s, we have two choices. It can be an M or an O. For the second character in s, we again have two choices. It can be an M or an O. Third character the same, fourth character the same, and so on. So for each character, we have two choices. Choices multiply, and we end up with 2 to the power of n different choices for the value of s. So what this gives us is the size of this loop is going to be 2 to the power of n. When n is 20, you can think of that as about 1 million loops. And then inside that, we have another loop over k. So the total runtime here is going to be k times 2 to the power of n, which is far too large. In the worst case, that ends up being about 200 billion. So we need a faster idea. And the final key observation that we're going to need to make in this problem is that they're actually not 200,000 moves that we need to analyze because most of the moves aren't unique. There are only n cubed unique moves. How do we know there are only n cubed unique moves? Well, each of the values x, y, and z have to be an index in the string s. Therefore, there are n choices for x, n choices for y, and n choices for z. So in total, we get n cubed unique moves that we can choose from. So instead of brute forcing over every possible move, we should only brute force over the unique moves. This leads us to the runtime of n cubed times 2 to the power of n. So assuming we're able to loop over every unique move instead of every single possible move, we can just get a barely efficient enough algorithm in order to get full credit here. One thing that we're going to have to be careful with, since we're looping over the unique moves, when we increase our counter for the number of successful moves, we don't want to just increase it by one. We want to increase it by however many copies of that unique move appear in the input. So one way of solving that issue is we can simply create a three-dimensional grid storing the frequency of every possible move. However, if you don't like the 3D grid solution, you could always use a map or a dictionary. However, I tend to like to avoid maps and dictionaries in my bronze solutions, so I've adopted a 3D grid here. Moving on to the code, since our runtime is near the upper limit of what is possible in USACO, we're going to be coding this in C++. So far, all we've done is read in N and K, and we've initialized a three-dimensional matrix to be all zeros. Again, you could use a map or a dictionary here instead if you don't like this three-dimensional matrix. But the key idea is the first dimension is going to store the value of X, the second dimension is going to store the value of Y, and the third dimension is going to store the value of Z. And then we are going to read in each of the k moves. Each move consists of 3 integers, and we are going to make one small transformation. If y is greater than z, we're going to swap it so that y is always less than z. So we're just sorting y and z. Since y and z are the same character, the two moves are identical, right? So we can always make it so that y is smaller than z because they both need to be o's. Doesn't change anything, but it does make our implementation easier. And then we're going to go to that slot on the grid, but we're going to zero index everything. So subtract one from everything. And we are then going to increase that counter by one. So this is saying I found one more copy of the move for these particular values. Next up, we're almost ready to begin our brute force search over all the possible values of S, but we need to define some helpful variables. We're going to define maximum to be the maximum number of successful moves we find. And obtain is going to store the number of strings that obtain the maximum number of successes. So these are going to be our two outputs at the end of the program. And now we're ready to begin our brute force search over all values of S. And this is the hardest part of the question and probably the hardest part of this particular contest. It's a very rare topic in bronze that you need to brute force over all strings of all binary strings. There's lots of different ways to do it. You could use n nested loops, so 20 nested loops in this case, each loop of size 0. You could use recursion, but that's generally considered to be a silver topic. Or the choice that I'm going to make is, since we have a binary string here represented by M's and O's, I'm simply just going to generate all of the binary numbers between 0 and 2 to the power of n minus 1. So there's going to be a one-to-one correspondence between these strings S and the binary numbers. So for example, moo I could represent with a binary number 100100, or moo MMO could be represented by the binary number 100110. So if you don't know binary, this solution is going to be a little bit tricky, but remember you could always fall back on that solution of 20 nested loops if you wanted to. There is a problem in the past that's similar to this, air conditioning number 2, where you had to brute force over all subsets of 10 air conditioners. And the easiest solution, or the easiest bronze solution for a question like that, was just 10 nested loops. So you could do the same thing in this question as well if you wanted to. However, we're going to go for a slightly cleaner solution that doesn't involve recursion. So by far the best way to solve this problem is recursion, but we're not going to use that since it is a silver topic. However, that does speak to the benefit of starting to learn some silver topics even while you're still competing in bronze. So it will be easier to implement questions like these that are quite challenging. But we're just going to loop t over every possible value from 0 up to 2 to the power of n. Note that this notation is just one way of calculating 2 to the power of n in C++. So if you see this funny symbol here, just note that it's just 2 to the power of n. Nothing too interesting there. We're going to initialize two vectors, a vector storing all of the indices of the m's and a vector storing all of the indices of the o's. And then we are going to save t in a value x, and our goal is to convert x into binary. Every value of x that's a 1, or every, let's say, digit or bit of x that's a 1, is going to store a value in either m or o, and then vice versa for the zeros. So for example, if x mod 2 is equal to a 0, I'm going to push back an index. This is just an append value onto m. So this is going to say, okay, digit I is a 0 in my binary number. So that's going to add 1 to the m's. And then if, on the other hand, the digit or the bit is not a 0, so it's a 1, I'm instead going to push back the index I onto the O's. So I guess in my code, the conversion to binary numbers is actually the opposite, where M's are represented as zeros and O's are represented as ones. So let me update the notes so it's consistent on both sides of the page. And then I'm going to divide x by 2, and that's going to let me calculate the next digit. So in case you've never seen this before, let's just run through this really quickly. Suppose we wanted to convert, I don't know, let's say the number 6 into binary. One way of converting 6 into binary is to get the smallest digit, so the ones bit, you could just mod by 2 and get 0. So the sort of first bit in your number is going to be 0, and then you're going to divide the number by 2 to get 3. When you do 3 mod 2, you get 1. So the next bit is going to be a 1, and then you're going to repeat. So you're going to divide 3 by 2 and round down, so you get 1. And then 1 mod 2 is 1. So the first bit is going to be a 1. So this is what 6 looks like in binary. If you've never seen this before, I recommend looking up how to convert between base 10 numbers and binary. You'll be able to find lots of great resources on that. But anyway, continuing on, the key idea is we've just filled in these two vectors with a bunch of indices. All of the choices, or sort of all of the zeros in our binary number got stored in the m vector. All of the ones in our binary number got stored in the o vector. And then we're just going to loop over every single choice of m and every single pair of choices for the o's. And then if the choice of the o's is not the same, we'll increase our count by however many values corresponded to this particular move. So we have a move I, J, K, and then we'll increase count by the frequency of that move. So if this move occurs very frequently in the input, we'll increase our count by a lot. If this particular move didn't appear in the input very much, then count won't change very much. And then all we have to do is update the maximum and obtain values. So if count is equal to the maximum, this means we have found a new string that produces the maximum count we found in the past. If that's true, we'll update obtain by increasing it by 1. Otherwise, if the count is bigger than the maximum, we're going to update the new maximum, and we're going to set obtain to be 1. We found one string that obtains this new maximum value so far. And then we just print out the maximum and the number of strings that obtain it, and we're done. So by far the most challenging thing in this question is simply looping over all binary strings of length n. If you've seen it before, it's easy. If you haven't seen it before, it's hard. So if you're looking for a good problem recommendation to practice this skill, I highly recommend looking at Air Conditioning 2. This is a nice, easy bronze variant of this same idea. If you're looking for a much, much harder question that also practices this skill, I would take a look at Robot Instructions from the Silver division. They both rely on this same idea, and it's a good source of practice going forward. So again, this is a pretty rare concept on a bronze exam, but it does occur on occasion. So thank you guys so much for watching the video. And if you have some nice Python solutions to this question, feel free to share them in chat. I know that everyone is always excited when there are good Python solutions for challenging questions like this. Thank you so much for watching, and bye-bye.